किशन सर, किशन सर,
Yeah, hello.
unmute your mic, sir.
Yes, yes. Can you hear me?
Okay, sir. Good afternoon, sir.
Yeah, good afternoon. Good afternoon. Can you hear me?
Yes, sir.
Okay, thank you.
So, good afternoon to all the participants. So now I request Vanajakshi madam to introduce about the today's speaker.
Good afternoon to everyone. A warm welcome to all the professors, associate professors, and assistant professors to today's FDP's afternoon section conducted by FDP Department of Lendi Institute of Engineering and Technology. I'm honored to introduce about today's resource person, Dr. Kishan. Dr. Dara. Dr. Dara Kishan received the BTech degree in Electrical and Electronics Engineering from Jawaharlal Nehru Institute of Technological University, Hyderabad in 2011 and MTech degree in Power Electronics from Jawaharlal Nehru Technological University, Hyderabad in 2013. He received his PhD degree from National Institute of Technology, Tiruchirappalli in 2018. Currently, he is working as an assistant professor in Department of E&E Engineering at National Institute of Technology, Karnataka, Surathkal, India. Dr. Kishan currently research interest includes power electronics and its applications in electrical vehicle wireless power transfer. He has filed 5 patents and awarded 2 of them and published 30 research papers in reputed journals and peer-reviewed international conferences. He is also an IEEE senior member and IAS, PELS, and IES society member. Dr. Kishan, he is also an active reviewer for various reputed IEEE transactions like IEEE transactions and reputed journals. He had guided 8 master level students in area of power electronics and currently guiding 3 masters and 6 PhDs in area of power electronics and its applications. Thank you. Now I am handing over the session to the Dr. Kishan sir.
Yeah, hello, good afternoon. Thank you, madam, for introducing me.
Okay, sir.
Okay. I hope you can see my screen. Please, can anyone confirm me?
Yes, sir.
Yeah, thank you. Yeah, good afternoon, everyone. So I hope everyone are good and enjoying this Ram Mandir establishment. Yeah. So yeah, good noon. So I will be just discussing about my research topic, that is wireless power transfer for electric vehicle battery charging applications. So specifically, I will be just talking about what are the power electronic aspects as well as what are the electromagnetics involved in this. So my presentation will just start with basic introduction to the EV, and just slightly I will give discuss about the charging infrastructure in EV. Then I will discuss about the wireless power transfer, then concept, and then complete design as well as implementation of this wireless charger. And then coming to the how can we do this bidirectional wireless power transfer, and then safety discussions. I mean, what are the electromagnetic interference as well as electric field interferences in case of if you really deploy this wireless power transfer. And just briefly, I will give you what are the future developments or future research scope we can do in this wireless power transfer, that I will just try to explain you. Yeah. So now just coming to the introduction, so we will just discuss how this EV is more advantage compared to our conventional IC engine vehicles. So one simple example, let us assume that we have an electric car as well as IC engine vehicle. Let us assume as a four-wheeler car. So on average, if you wanted to run for 1 kilometer, let us assume 1 kilometer distance, if you wanted to travel, we will just take two cases. One is this is EV, this is IC engine vehicle. So for any vehicle, an average of 120 watt-hour energy is required to travel the 1 kilometer distance. So if you just, I am just coming from back, I mean, output to the vehicle output to the coming to the input side. So in order to get this 120 watt-hour energy for an IC engine, we have to provide 520 watt-hour energy. If you see for the electric vehicle, that is motor drive will be involved right over here. So in that case, we required 150 watt-hours. So for this 150 watt-hour energy generation, let us assume you have a thermal power plant. So where an average of 330 watt-hour energy is required. So in order to get this 120 watt-hour energy, so at the input of this thermal power plant, we required 330 watt-hour. So overall, if you observe the efficiency, so 120 by 330, it comes around 33 to 35%. So similarly, if you see for the IC engine vehicles, so whatever we are talking is crude oil input. So where an average of 950 watt-hour energy is required. So if you see right over here, 120 by 950. So that comes under around 10 to 12%. So if you compare this efficiency, we can say that the EV is 3 times efficient than our conventional IC engine vehicle. So as efficiency, if you talk, so then if you see about the fuel cost, so if you see in case of EV, it will be less compared to the IC engine vehicles, as well as the noise. EV will be noise free, and you will be having less maintenance compared to the IC engine vehicles. So now coming to the actual problem. So in EV, there will be a limited driving range. But in case of IC engine vehicles, you can travel longer distances without any interruption, right? I mean, within few seconds or within few minutes, you can refuel your petrol tank and you can travel. But in case of EV, that's not possible. We have to wait for several hours, you can say, to fully charge the battery. So that is the biggest problem. So as this is the major advantage, you can say. That's why we are going behind these EVs. Okay. So now if you see the current status of EVs in India, so actually as per our 2030 target, so actually we wanted to make it as 100% EV nation, but still we are lagging. So as government is initiating so many schemes, right? So 0% down payment, and we also have for the development of the charging infrastructures, we are getting more incentives, right? So these are the things we can see. Still, and even though this, so we can see on the roads currently there are few vehicles are available in the market. You can see particularly for the public transportation. I think in TTD they have fully 100. I mean, there are a lot of buses. They have. They have using it currently EVs, and as well as coming to the normal rickshaws, still you can see a lot of, I mean, popularly you can see in the Jaipur and this Nagpur, as well as few, few you can see on the roads. So the problem is that only the charging infrastructure. So now if you see conventionally, what is the charger will consist of, right? So I'm just talking about high power battery packs where we need to charge our batteries either in the two modes of operation, constant current or constant voltage modes of operation. So how we will choose this constant current and constant voltage means, let us take your battery, you have a 60 volts of battery pack, that is assumed. So we know that this is the nominal voltage of the battery. So if you are having the less, I mean, SOC is fully charged, so your battery voltage will be around 62 to 64 volts. Let us assume for 100% SOC, it will have 64 volts of battery. I mean, voltage will be there. So, but in case of if we have lower voltage, like if you have the 40%, 30% SOC means if you will be having a battery voltage, nominal voltage of 58 volts to 55 volts in the range. So in order to in general case, so from 0 to 80% of your SOC, we will be charging in the constant current mode, and from 80 to 100%, we will be charging in the constant voltage mode. So these are the two things we will be following for battery charging. So in order to get this CC-CV modes of operation, conventionally we will be using a DC-DC converter, to regulate this constant current and constant voltage modes. So actually we have a grid which is AC source, which is single phase AC source, let us assume. So depending upon your battery requirement voltage, if it is a 60 volts, then obviously we have to do from 230 volts to lower voltages. So we required in a transformer. And then this AC input filter, what is the purpose of this AC input filter is, as we are introducing these non-linear components, it will introduce the harmonics. So to limit that, we will be using AC filter. So as it is a AC, we need to convert into a DC to charge the battery. So we'll be using rectifier. So this DC link capacitor to make it as a stiff DC, that is a constant DC voltage. So actually rectifier will have pulsating DC, right? So to make this as constant DC, we will be using a DC link capacitor. Then as I mentioned about the CC-CV modes of operation, we will be using a chopper, that is nothing but a DC-DC converter. Right. So this is the general conventional battery charger topology. We will be using it. Right. So now if you see for the particular EV battery charging application, depending upon the power level as well as input voltage, there is a certain classification. This classification has been defined as per the SAE standards. You can say Society of Automotive Engineers. So if you have a 120 volts of AC socket, so if you charge, let us assume this our car, four-wheeler electric car, four-wheeler e-car. So if you charge your vehicle for 1 hour with the 120 volts AC socket. So if you charge 1 hour, and averagely you can travel 2 to 5 miles. So, and this type of infrastructure, charging infrastructure, we can use in homes as well as some workplaces also we can deploy this level 1 chargers. And coming to the second level of level 2 chargers, which will be charging through a 240 volts or 230 volts AC sockets, so which can use this charging. If you charge 1 hour, as our whatever the example we are talking, electric car, if you charge for 1 hour, so it can deliver an average of 10 to 20 miles range. And this type of charging infrastructure we can use in homes, workplaces, as well as in public charging places. So now coming to the level 3 chargers, which are generally referred as fast chargers. So we can say this, it is a like input source is a 3-phase source, you can assume, and generally for like 450 into 480 or something for 3-phase voltage range. So in this case, it is mentioned as a fast charger, right? So it's required highly specialized equipment, like, and high power equipment is required. And while handling this, little trained people is required. Like you cannot simply use it wherever required, but this has to be particularly designed and particular places only we can use. Like public charging stations only we can use. And as well as this DC fast chargers requires heavy cables, like as it is a fast charging, that means we are going to inject a high amount of currents. So that's why we required heavy gauge cables. And so as one example, we are talking e-car. So if you charge for 20 minutes charge, you can travel an average of 60 to 80 miles. This is an average estimations for the different levels of charges for the travel distances. Okay. So if you see overallly, so in the AC normal charging, you can say level 1, level 2 chargers, which will use 110 volts and 220 volts AC source. So in order to charge fully electric car, so that electric car need to be charged for an average of 4 to 10 hours. If you wanted to make your electric car fully charged with the level of level 1, level 2 chargers, so it requires at least 4 hours to fully charge the battery. So this level 1, level 2, we can install, we can use, or we can install at homes, and we can install at the public spaces. So there is no requirement of large installations. So due to this 4 to 10 hours of charging time, still there is a range anxiety. That means if you wanted to travel for the longer distances, you have to wait for an average of 4 to 10 hours. So as apart from this level 1, level 2, we have seen this fast charger, DC fast chargers we have referred. So in this case, you can charge your vehicle within the 15 to 30 minutes, 15 to 30 minutes. So now the question is that, so if you wanted to charge, let us assume that you have a 24 kilowatt battery pack, one electric car. Let us assume this electric car has 24 kilowatt hour battery pack. So now you are trying to make this 24 kilowatt hour battery pack to charge in 15 minutes, to charge in 15 minutes. So that means an average of 24 into 15 kilowatt hour energy is required. So that means an average of 96 kilowatts energy is required. 96 kilowatts. That means when a single car, single EV, it requires 96 kilowatt hour energy. Now you assume that you have multiple number of vehicles you are going to charge at a time. It isn't simple 10 vehicles for a particular city, 10 vehicles. That itself it demands 960 kilowatt hour energy. That is approximately 1 megawatt energy, right? So that means it will create burden on the grid. It may causes grid failures also. So another problem is that, so you are going to fast charging means fast charging. That means you are going to inject high currents in your battery, high currents in your battery. So every battery will have its own current capability, right? So we are trying to inject higher amount of current. So what will happen means if you do this frequently, so it will degrade your battery lifetime. Can say. So this is the problem with this fast charging. So if you see orally level 1, level 2 chargers, we need time to charge fully the vehicles. If you take the fast chargers, this bad power demand on the grid will increase, and it will also creates the battery degradation problem. So then how can we overcome? So I think you may be heard about this battery swapping. Battery swapping means just interchanging your battery with a fully charged battery with, I mean, whatever your less SOC charged batteries with the fully charged batteries. What we will just interchange it. So, but now I have a question that, so now we, as the manufacturer point of view, if you take different manufacturers will take their own specification. Someone may follow some standardization. Someone may follow something like if you take the recent vehicles, one vehicle will come with a 400 volts battery pack. One vehicle will come with 800 volts battery pack. Someone may come with 120 volts battery pack. So this specification will differ for each vehicle. I mean, each manufacturer's vehicle. So in that case, what will happen? We cannot make particular standardization. The standardization will be difficult to these battery swapping station owners. So, and then what we need, we have to do a lot of investment on the battery packs. Apart from the EV itself, if you see overall cost point of view, EV will a higher cost compared to IC engine. If you see, instead of battery swapping station, there is a lot of bad investment required on the battery packs. So it automatically creates burden on these owners, right? So now, if you see in terms of the space requirement as well as manpower for operating the battery swapping stations, those everything will come into the picture, as well as the biggest thing is safety as well as reliability is also problem for this battery swapping stations. So now we have problem with level 1, level 2 chargers. We have problem with these fast chargers. We have problem with battery swapping. So then what can we do? So now I just can think of this wireless charging. If you do frequently, you can do this wireless charging on the highway, so that you can limit the battery. I mean, you can increase the battery SOC certain percentage, and as well as it is you are doing frequent charging, that means you are not going to make your battery to fully discharge, so that your battery lifetime will be good compared to when, if you see, you have a battery when you are completely discharging is one case, and another case what I am doing is I will discharge for certain limit only. Let us assume that till 40% only, again I will charge to till certain 70-80. So if you compare these two, which battery you are completely discharging and which battery you are making 40% discharge only, and from there you are charging it. So in these two cases, the battery lifetime will be good in case of which you are not completely discharging. So that is the advantage in the frequent battery charging, right? So as if you see orally the issues with these conductive, that means plug-in battery charger or battery swapping station. So electric safety is concern. So there will be a possibility of electric shock due to the rain or dust or any short circuits. And this charging station, if you take the fast charging, there is a lot of space is required for the maintenance. And in some cases, if you are having like level 1, level 2 charges, there may be a damage in these your plug, or sometimes you can think that someone can steal easily. And this charging swapping stations need lot of the investment as well as a lot of space. So as I'm talking about, what is a simple solution is that wireless charger, we'll just deploy the wireless charger on the road. So wherever possibility is there for stopping for certain time interval, just like traffic signals or bus stops, where we can charge certain amount of SOC of your battery, so that will remains good SOC for your travel distances. So overallly, if you see the classification of this wireless power transfer or the power levels, in terms of the power levels, if you see, so in terms of the power level, you can say that high power, medium power, and low power. So and then second way of classification, you can say that in terms of the medium, which medium as we are considering to transfer the power. So let us take, if you are low power applications and you have very long distances, low power means in terms of milliwatt and maximum of 10 watts, you can assume. So in this electromagnetic radiation, that is simply, you can assume that microwave and laser power transfer. So those can be used for very low power applications, and you can go for certain kilometer distances. And then another classification is that electric induction. Electric induction is nothing but, see, electric induction, as everybody, I hope everybody knows about the capacitor. So we will be having two parallel plates capacitors. So in case of the medium power applications and lower distances, so there will be a separation distance between two parallel plates, right? So in this capacitive power transfers, we will be using two pairs of two parallel plates, right? So these two parallel plates and these two parallel plates. So here, so the medium will be used as electric field, and the distance between these two parallel plates will be very small. You can say very few you can say few distance only we will use this. That is what second classification, which is electric induction based power transfer. So depending upon operating, so there is a classification resonant electric induction based, that I will talk about the resonant. So don't worry about that. And then another classification is that magnetic induction based. Magnetic induction based is like inductive power transfer. So what is this inductive power transfer is that we will be having the I hope everyone knows about the transformer. So this generally this transformer will wound on a common magnetic core, right, like this. So where primary winding and secondary winding will be there, and this whenever we excite this primary winding with a V1 voltage, so there will be an E2 induced EMF due to the flux generated by this primary winding, right? As the source is an alternating, so the flux generated by this primary winding will be alternating. So when there is a rate of change of flux, then will be an induced EMF. So when this flux is linking to the secondary, so there will be an induced EMF. So when you connect to the load, so automatically the current will transfers from the primary to secondary depending upon your this winding turns ratio. So just assume that instead of there is a common magnetic core, if you assume there is no magnetic core between these two, the primary and the secondary. Sorry, 1 minute. So now the primary winding and the secondary winding. In the transformer, we had common core, but in now I've just removed this common core and separated with an air with a distance of d. Let us assume. So as I am exciting this, so it will produce its own magnetic field, right? This primary winding. So now what I'm doing is I am bringing this secondary winding between this vicinity of this magnetic field. As we know that this magnetic field is alternating in nature, as the source is alternating. So as it is linking to this number of turns, so there will be an induced EMF automatically. So when you connect to the load, then automatically there will be a current flow from the primary to secondary. Okay, so right, you can see right over here, just physically imagine how it will be. So this you can bottom one, this block layer here, you can assume it as a transmitter, and this one you can assume it is a receiver. So now, whenever you excite this, this flux will be generated. So this flux lines you can see. So whenever this linking to this receiver, so when you connect to the load, so there will be a current flow from this source to load. So in EV application, how can we use this? So generally the coils will, the primary and secondary windings will be wound on a common core, right? So we're just winding this copper wire on one limb, another limb. Secondary will be another limb. But how can we deploy this for the EV application? So in this application, particularly, we should have a planar surface, like planar structure, which can produce us the magnetic field in the vertical direction. So right, you can just physically see right over here. So the coil structure should be have planar like this, and the field should be generated in the vertical direction, so that it will interact with the receivers, and we can, whenever we connect to the load, there should be an current flow from the primary to secondary, right? So if you see an electrical equivalent circuit point of view, so as we have known that, so we'll be having the primary winding and secondary winding. So these two are the primary and secondary, this L1 and L2, two windings with the internal resistances R1 and R2, we can assume it as, and when it is just connected to a load resistance RL. So my primary intention right over here, it is I should know what is the amount of the efficiency I can get. So how can I determine that? So by knowing the equivalent circuit, I can just apply the KVL, KCL equations, and I can approximately can compute the power equations. And as the efficiency, we can see output power, that is load power divided by input power, and we can observe what are the parameters will be there in the efficiency expression, and in what way we can improvise that efficiency, right? So first, as a theoretical step point of view, we should know the equivalent circuit, so that we can find the powers, the load power and input power. So this is just similar to our transformer. So the T equivalent circuit of this WPT system, IPT system, inductive power transfer system, IPT, right? So here this L1 is the primary inductance, primary coil inductance, L2 is secondary coil inductance, R1 and R2 are the internal resistances of those primary and secondary. So now this equivalent circuit, if you see this in T equivalent circuit, we will be writing this terms, this inductance as L1 minus M, this one as L2 minus M. Just apply the KVL on the both loops. and you can derive these equations by applying the KVL. So my intention is that input power and output power. So if you overall see the input power and output power ratios are like, you can, so after simplifying you will be getting like this. Okay, so in this efficiency expression, you can see that in the denominator, in the numerator, I have omega m and RL. In the denominator also omega m, RL, R2, R1 and omega L2. Okay, so now this expression point of view, this efficiency can be, I mean, you can achieve the maximum efficiency as when this omega is higher. Omega is, what is this omega? This omega is nothing but our source frequency, source angular frequency. Omega is equals to 2 pi f. This is the source angular frequency. And the second term m is the mutual inductance, between this primary and the secondary. And this RL is the load resistance. So R1, R2, as we have already seen, what is that? That is the internal resistance of the transmitter and receiver. So these resistances will depend on what type of the material we are using for the construction and what is the shape of the coil we are doing. So we can say that the efficiency can be higher. Efficiency can be higher when the internal resistance are lower compared to RL, and the mutual inductance M should be high, and the angular frequency omega of the voltage source should be high. Okay, so these are the things we can tell that efficiency will be higher with these three conditions. So apart from this, there is a denominator, another term which is omega L2. So we will discuss about this later. Okay, so if you write this efficiency expression in terms of the coupling coefficient, right, K is equals to m by square root of L1 L2. So in terms of, you write that, and the quality factor. So this is the efficiency expression. This is another way of mathematical expression. Okay, so right now you may have a question that in EV application, if you take generally, if you take the transformer, we will be having the common core. So on primary side of the limb, we will be winding the copper wire. In the secondary side, we will be doing that. But as I have already told you that in case of EV application, we should have the planar structure. The structure of the primary and the secondary winding should be planar magnetic, right? So now another constraint is that the flux generation from this winding should be perpendicular. It should be vertical direction, so that the height, the distance between the application, depending upon the application, the distance requirement will differ. So we should see it should give more height so that we can use it for the any application. So based on the literatures available, there is a two classification for these planar coils which are used in these wireless power transfer, that is polarized and non-polarized coils. Polarized and non-polarized, what does this mean is that, so in simplest way you can say that the two terminals of this coil, that is the, you can say inductor, can be used as any phase or neutral. But in case of polarized, particular terminal only we have to use that phase. The current direction, the entering current should be in that particular direction only, right? So if you see here, the non-polarized means a spiral circular coil. Spiral circular coil. So I will show you one how it will be looks like theoretically. And another example you can say spiral square coil or spiral rectangular coils are non-polarized coils. In case of polarized coils, you can say this as DD and this as DDQ. DDQ. So these are the non-polarized coils, you can say. So right, in as a beginning, as we have discussed about that efficiency which has omega term, m term, RL term, and in the denominator L2 was there and R1, R2s were there. So these, as a theoretical prospect, I should know what is the generalized efficiency to design an APT system. So in this case, omega, we will talk about this omega later on, this m, RL, and here L2. So we should know these inductance of the secondary. So right, inductance. So that means if you are using the spiral circular, you can just see here, this is the spiral circular. This is the copper wire. This. So like this will be a spiral circular coil. So where in inner diameter or inner radius and outer radius, you can observe right over here, the inner radius and outer radiuses. So how can I compute the self-inductance of this spiral circular coil? You can see right over here, the self-inductance, which is equals to n square r square by 8r plus 11w, where n is the number of turns, n is number of turns, and r is the mean radius of this spiral coil, mean radius, that is 1 by 2 of r naught plus r in, r naught plus r in, that is outer radius plus inner radius. Similarly, the depth of the spiral circular coil, that is outer radius minus inner radius, that will be gives your total thickness of the coil, right? So by this you can compute this self-inductance of the coil. Similarly, if you have spiral square coil, you can use this. So these equations are actually based on the Wheeler equation, which he has derived the equations for the all type of the shapes. You can compute the self-inductances. Okay, so this the denominator part, which is L2, we have done now, right? Now coming to this R1 and R2, right? R1 and R2. R1 and R2 are the internal resistance of the primary and secondary. We can refer it as the transmitter and the receiver also. So how can we compute this? Now I have an interesting question that, so as we mentioned that efficiency is directly proportional to omega here right over in the expression. So this omega should be higher so that efficiency will be higher. So till what level we can go? So there is, for the IPT system, there is a standard which is referred as SCAE J2954. It is a standard which is Society of Automotive Engineers wireless power transfer standard. They have defined the different power levels as well as the operating frequencies. So the operating frequency should be between 80 to 100 kilohertz, 100 kilohertz. But most of the systems have designed for the 85 kilohertz only. So as this is a 85 kilohertz is our switching frequency, there will be other cases where for the efficiency improvement, we will be operating our system, the above resonance. So that we will talk in the power electronics point of view. Here only we will just see how can I compute this R1 and R2. And as I'm talking, it is a high frequency. So if you use your simple mono wire, normal copper single strand wire, and it is a high frequency operating system. So how will be the this high frequency effect on the mono wire? So if you see overallly, as you may be heard about the skin effect and proximity effects, right? As the frequency increases, the system will have the skin effects and proximity effects. So how can we avoid that? So instead of using the mono strand wire, we will use multi-strand wire. So specifically designed for the high frequency applications, which are generally referred as leech wires. Okay, for designing these inductive coils, we will be using this leech wire. So what is the advantage in this? So advantage is that it will have reduced skin effects. So compared to the mono wire, so this multi-strand wire will have the better temperature control, and it will have lower the AC resistance, overall AC resistance compared to this. Okay, and you can say that due to this, you will be having low this copper losses compared to this mono wire. So how can we compute this AC resistance and DC resistance for a multi-strand wire? That is what this here I have given the mathematical expressions. So for the DC resistance, you can see 4 is rho C by L total. This is the total length of your wire which is used in your circular spiral or whatever the coil structure. And this pi is the normal constants, and n is the number of the strands in your system, and this ds is the diameter of the strand, diameter of the each strand. So similarly, how can we compute this AC resistance means, which is a frequency dependent? So this is the equation. Okay, so this R1, R2 and L2 we have computed. Now left over is the M, right? The mutual inductance. So listen here carefully. So if you are really interested in this electromagnetics, like computing the inductance parameters and the resistance parameters, here it is a very good research scope. So let us assume that I am just considering only one case. So later on you can think how can we find this mutual inductance analytically for the different shapes as well as the different configurations. Okay. So let us assume these are the different literatures, leave about that. So now you can see. So only one case I am considering. I have like this two windings. This is the primary, that is the transmitter. Let us assume this is the receiver, right? So with the diameters of A and B, you can see here A radius and B radius. This is the transmitter, you can say. This is the receiver Rx. Okay. So now I just wanted to find the mutual inductance between these two if they are separated with a distance of Z. Okay. There is a Newman's equation which he has derived this final equation, which is having the parameters of A square, B square, that is where A and B referred to the radius of the transmitter and receiver, and this Z is referred to the vertical distance between these two. Okay, so if you have a single turn like this, single loop, you can say single turn, single loop. If you have like this, so you can directly put this equation and we can compute the mutual inductance. Now the question is that in case of the IPT system, you will be having the coil like this. So in this case, what we'll do is each turn like this till here will be considered as a single loop, you can assume. So like this, I will be having N1 number of turns in the transmitter, N2 number of turns in the receiver. So then how can I compute this? So what I can do is the all possible, this equation only, I will do it for the all individual turns and finally I will add up that, sum up that. So finally you can use this equation and the corresponding figure you can see right over here, which is having N1 number of turns in the transmitter. So this is the transmitter N1, this is the receiver N2. So the summation of I1 is I is equals to 1 to N1. That indicates transmitter first turn to N1 number of turns and the receiver I1 turns to N2 number of turns. So each combination when 1 1 1 1 2 1 3 1 4 like that, again 2 1 2 2 2 3 2 4, all combinations, and you will be adding up that. So you will be getting the resultant mutual inductance between these two coils. Okay. So now another interesting question. So you have deployed this in EV on the road, right? This transmitter will be on the road, TX will be on the road, and this RX will be in the vehicle, right? So this vehicle, this is the vehicle which is traveling. So this distance between these two is D. So there is no guarantee that this vehicle will come and perfectly match these two configurations, right? There is a possibility of mismatch between these two. So yeah, please 1 minute. Hello. 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 Hello.
Sir, your voice is audible, sir.
Madam, I'm just having the presentation. I will just join the meeting 10 minutes later. Okay. No, just outside online. Okay. Okay. Yeah, sorry.
Okay, sir. Okay, sir. We can start now.
Yeah. So as we are discussing about this vehicle real-time application, so where transmitter will be on the road, receiver will be in the vehicle. So there is no guarantee that this vehicle coil position will perfectly match to this transmitter. There is a possibility that this may go forward or backward, or in some cases it may have inclined angle also. So in these type of the cases, how can we compute the mutual inductance, which is very, very important parameter for the IPT system, right? So this computation of this M is very, very important. So if you have different structures, as I have beginning, I have told you that possible ways of this transmitter, I mean, this coil structure configurations. It may have spiral circular, it may have spiral square, it may have DD shape, it may have DDQ shape. So whatever it may be the case, there will be some mutual inductance. Then analytically, how can you determine that, right? So that is what here previously I have given some literatures. They have computed this. So in this particular applications, how can we compute the mutual inductance? This is the, I mean, I can say it is a very good research scope for doing lot. Okay, right. So now that is the one research scope, one research gap I can say. Now I'm just discussing one case study. Okay, so as we till now we have done the theoretical calculation, right? That is L1 calculation, M calculation, R1, R2 calculations. We have done it. Now I wanted to know whether those calculations are correct or not, right? So how can I compute in simulation point of view? How can I do that? So there are certain simulation tools which we can do these electromagnetics modelings. If any researcher are working on these motor drives, like design of the induction motor or BLDC motors, they will be knowing this. So this like ANSYS Maxwell and this COMSOL and this HFSS, which are finite element modeling simulation tools where you can design this electromagnetics and you can check your performance of that corresponding machine or inductor or coil. Okay. So for this, if you see right over here, now interesting thing, as I have previously discussing, as if you are going for real-time EV application, real-time EV application. So in that case, we should have strong coupling between, we should create strong coupling between the transmitter and receiver, right? So how can we increase that? So you use a ferrite support to the coil so that it will give you maximum flux. I mean, flux path will be, I mean, the flux generation transmitter will be, it will be creates more. I mean, it will creates appropriate flux in the proper direction, you can say. So you can see right over here, this orange color is a copper wire. That is whatever we have referred, it is a leach wire. Okay, leach wire. Then you may have, what is this green right over here? So this green is a ferrite core, so which gives us the flux direction proper way, or you can say it will increases the flux generation. Now this third layer, if you see this ash color, so this is a chassis, which is generally a steel material. Why this steel is required right over here? The important thing is that as you are deploying this in EV, so there will be a possibility of eddy currents in the neighboring devices. So right, so in order to make proper shielding, in order to make or in order to reduce the magnetic field interference with the neighboring devices, we will use this steel material so that it will diminishes the leakage fluxes. Okay. So now another thing is that previous case, one example, spiral circular I have discussed. So if you design this in, this is the one example for ANSYS Maxwell. So where this transmitter and receivers are designed in this, in that, you can see this magnetic flux, which is generated by this transmitter. You can see that right over there. So similarly, this one case is that when this receiver is moved away in the X direction, you can see the amount of the flux which is linking to the receiver coil, right? So this is one example, one case study as I mentioned. So one leach wire which 0.1 mm, 1500 strands with the overall wire diameter of 0.5 centimeter. And then you can see this is a spiral circular coil. Okay. So this ferrite, as I have mentioned, the second layer is ferrite core, right? So in order to do this weight optimization, I have used this ferrite bars. Instead of using entire ferrite core, I have used this ferrite bar. So similarly, one spiral square coil. This is spiral circular coil. Okay. So now overall, if you see the magnetic flux density, the values, maximum values of flux densities. So there are different possible alignments. So one is perfectly alignments. Both the transmitter are and receiver are perfectly aligned with each other. That is referred as perfect alignment. Planar misalignment is transmitter here, receiver little moved away from the transmitter. Then second one is, third one is angular. Angular means tilted angle. There will be a tilted angle in the this theta, you can assume. So there will be in the receiver coil. The fourth one is both these combinations. So I have taken these three different case configurations. Which one is, first one is only wire with this spiral circular shape. So we can see corresponding maximum flux density, which is 43.053. Now second one is only with core, with the ferrite core bar support. So in that case 85.04. And the last case, so in the last case, both with core and chassis. So in that case, you can see which is 66.85 microtesla. So overall, in the real-time application, we will be using this configuration with core and chassis. Okay. So now, in order to validate our computed mutual inductance and self-inductance L1 and L2. So practically, how can we test this? We can do this self-inductance with LCR meter, right? LCR meters will be there. So simply you connect to this your copper, whatever the winded. So it will give you operating the correct exact what is the self-inductance of that that coil. So now, how can you compute this mutual inductance experimentally? So experimentally, you can do with the help of open circuit test. Open circuit test. That means these two coils will be there. The secondary will be simply open circuited and it's connected to the multimeter. So where you will be having the open circuit voltage. So with this open circuit voltage and primary current, you can measure this M. Okay, M is equals to V2 OC by omega I1. How it comes? So the secondary voltage V2 OC is equals to omega M I1. This is the induced EMF in the secondary. Okay, so with this you can connect. Or you can do another test, which is two inductors. You connect in the with the separation distance. First you connect in the series aiding connection, and another case is you connect to the series opposing connections. L equivalents 2 will be there. You add up those two, then you can write this M is equals to L equivalent 1 plus L equivalent 2 by 2. You can do and you can compute the corresponding mutual inductance. Okay, this is one case study example. I am not going to discuss. So overall, you can see the three results: one analytical and FEA and practical. Okay, right. Now, this is what I just told you in the beginning. My research topic is, my presentation topic is wireless power transfer, bidirectional wireless power transfer, electromagnetics and power electronic prospects. So the part of electromagnetics I have done, that is how to compute the self-inductances and mutual inductances, and how to choose the coil. But this, I mean, how to choose the coil is, that is your own choice, that depending upon your application, depending upon your dimension available for your vehicle chassis, those considering those constraints, you can choose the coil. So most of the planar coils will be used for the static charging applications, and for these quasi dynamic and dynamic charging applications, so the tracks will be designed. And in case of quasi dynamic charging applications, specifically this DD and DDQ coils will be used. Okay, so that is about the electromagnetics. So I'm just open for the discussion about this electromagnetics. So anyone have question, you can about the electromagnetics. If you have any questions, please, you can. Participants, if you have any questions, please let me know about this electromagnetics. For this, we can just post in the message box also. the session is not yet over. I have one more continuation topic, which is power electronics prospect. I just wanted to know if you have any queries, you can about this, whatever we have done.
Dear participants, if you are having, interact with us by unmuting your audio.
Okay, anyway, so I will continue for the next topic. That is power electronics prospect. Sorry, someone is talking.
Anyone have doubt? Okay, sir, you can continue.
Yeah, fine. So now, as we have seen that efficiency expression, this is the same expression, don't confuse. So this denominator I have written, this will come here. So this will multiply with this omega square m square, and here also numerator omega square 1 square. So the same expression. So in the denominator, as we have seen that efficiency can be achieved higher with omega by increasing omega and m, and R1, R2 should be lower. So now another way of possibility of improvement in the efficiency is that this denominator we have omega L2. So this is inductive reactance. So this inductive reactance, if you compensate with an appropriate capacitance with inductive capacitive reactance, sorry, capacity with this inductive reactance with an appropriate capacitive reactance. If you make it cancel out each other, then you can improvise this efficiency, right? So this process is called as right over here compensation. So depending upon the, I mean, if you see why we need this orally, if you see why we need this compensation, that is, first thing is this inductive reactance will be neglected. It will make it a zero, so that overall efficiency will be improvised, right? Then another thing is that the VA rating ratio, generally for in a system design, we will be making this as unity. So in order to make this unity, I mean, if you derive this VA rating ratio, you will be having here L1, L2, and here L2. So this, if you compensate with an appropriate capacitor, that is omega C, this 1 by omega C, so that this will become 1. So you can say that if you use appropriate compensation technique, so we can make the VA rating ratio as 1, right? So apart from that, orally, if you see the advantage, I mean, you can say the requirements, why we need this compensation is that to maximize the power transfer. Maximizing power transfer is nothing but right over here, it is improving the efficiency, right? And to maximize the VA rating of the power supply, to maximize the VA rating of the, sorry, to minimize the VA rating of the power supply. And then another application is that, another advantage is that, so in battery charging, EV battery charging application, we need this CCCV modes of operation, right? So this CCCV modes of operation can be achieved with appropriate compensation topology, right? So there are basic compensation topologies which are series compensation here, series parallel compensation, parallel series compensation, and parallel compensation. For these all compensations, efficiency expression will vary. So this is about overall series compensation. Here, if you see, this omega L2 term has gone in the denominator. Okay, so with an appropriate capacitor compensation. Not only with compensation, that compensation we have to operate at proper frequency so that inductive reactance and inductive capacitance will cancel out each other. So to make this possible, we have to operate at resonance. So that's why these IPT systems are referred as resonant IPT systems, resonant inductive power transfer systems. Okay, so apart from this basic compensation topologies, so generally this in the secondary parallel will be used for the CV, and series capacitors will be used for CC modes of operation. Okay, so how to design these capacitor values, C values for particular IPT systems, that you can find it in the literatures. So right, so orally, if you see what will be there in these IPT systems, let us assume from this you have a DC source, and now I wanted to charge this battery with CCCV modes of operation, right? So this is a DC source. As our IPT system demands high frequency source. So this DC will be converted into a high frequency AC. This is a HFI, high frequency inverter. So which will be connected to a, I have just considered series compensation. So the primary is also having series capacitor to this, and then secondary also it has series capacitor to this. So when it is connected to this high frequency inverter, so this current will flow through this, so it will generate the magnetic field, so which will be linked to this receiver, and it is connected to the capacitor, and then here it is, you see the current and voltages will be high frequency. So then we need to convert into a DC in order to charge the batteries. So right, so this high frequency AC will be converted into DC by using a diode bridge rectifier, and then in order to regulate the battery charging, you can connect a DC-DC converter or a DC-DC, which is referred as chopper, so which will be connected to the battery to regulate the battery charging current and voltages. And this controller will be used for this secondary side DC-DC converter, and this controller will be used for the primary side converter. And there will be a wireless communication to start or stop the charging. So now, what is the advantage of this, the IPD system overall? You can say that automatic charging can be possible. That means there is no involvement of human to plug the charge, to switch on that. There is not required. It's automatically you can charge. So you can say that overall it is more convenient compared to the plug-in battery chargers. So if you see overall the major components, the first one is high frequency inverter, then inductive coils, rectifier, compensation capacitors, the DC-DC converter, and then communication system. So this is general H bridge, how it will be operated. So we'll be having a square wave, so which will be fed to the primary coil of the system. Then this is about the buck converter design. This everyone I hope knows how to design the buck converter and how to design a controller for this buck converter to charge this CCCV modes. Okay. So as efficiency is the crucial one. So in the IPT systems, most probably we will be using some advanced devices such as SIC or GAN devices, right? So the research scope is also right over here available. So design of the driver circuits for this appropriate SIC devices. Then small signal modeling of the DC-DC converter, right? To make CCCV modes of the charger. So this is a CV mode transfer function of the DC-DC converter, where output voltage divided by duty ratio. Similarly, for another loop, we have to design I0 by D, right, for making CC mode of charging. This is one experimental setup. You can see right over here. This is a coupled coils. This is a DC source. This is a H bridge inverter. This is the resonant capacitor. Here it is a resonant capacitor. This is diode bridge rectifier. This is DC-DC converter. Okay. Right. These all are general power losses in the system: inverter losses, coil losses, diode bridge rectifier losses, and then DC-DC converter losses. So orally, in the DC-DC converter, you will be having conduction, switching, and if you are having inductor, the iron losses and core losses in the inductor. Okay. Right. So leave about that. So if you see overall the power converters in the unidirectional IPT system, we will be having the high frequency inverter, then we will be having the diode bridge rectifier, and then DC-DC converter. Now to make it a bidirectional, let us assume a DC to DC case. You have input source as DC, output source as DC. Now output battery is also DC. So in order to make that, we should use the bidirectional converters. We should be capable of both directional control, right? So in the primary side, this is a high frequency inverter, right? So this is a high frequency inverter. This is the compensation. This is the coupled coil. Again, this is the compensation, and this is secondary side rectifier. First case, from DC grid to battery. In this case, primary side converter should work as inverter, and the secondary side converter should work as rectifier, right? So this AC need to be converted into DC, and this battery charging regulation will be done with the help of this active switches. In the reverse case, from vehicle, this is the vehicle, right? So vehicle to grid case, this converter will act as a high frequency inverter, and then again same, this is a compensation, this inductive coils, again compensation, this converter will act as a rectifier. So in this case, there are certain control methodologies which can achieve this battery charging with the help of this converter itself. Okay, so now coming to the control methodologies. See, we have primary side a high frequency inverter HFI, then capacitor, then coils, then a diode bridge rectifier. Let us assume here I have diode bridge rectifier. So this battery charging regulation need to be done. So we can say there are three methods to regulate this battery charging. The first one classification is we have seen that we will be having here additional DC-DC converter which will control this. Now the second case is that we will be not using any active switches on the receiver side. We will be controlling only this high frequency inverter and we will be regulating this battery charging. How can it possible? Means we have here high frequency inverter force active switches. Here the output is the high frequency output. So depending upon the current in this, here will be induced EMF that will give appropriate here voltage, right? So this voltage can be controlled at the high frequency inverter output by varying the frequency. You can say this as variable frequency control. So by varying the frequency, you can regulate this battery charging. So first case is variable frequency control. Then second case is fixed frequency control. In the fixed frequency control, what I will do is I will control the switching time period of the each switches. So here again, there are different methods. The first one is phase shift control method. Second one is asymmetrical clamped mode control. This phase shift control is nothing but symmetrical phase shift. That is nothing but both positive and negative half cycles will have equal zero level here and here. So that what will happen? No? So this zero voltage switching will happen. So this zero voltage switching will make us the switching losses zero so that overall system efficiency can be improved. How can it will be possible? Means the inverter losses will reduce, inverter switching losses will be reduced so that overall efficiency can be improved. So by controlling this zero level equally on for the positive half cycle and negative half cycle, we can achieve the output regulation, output voltage we can control according to this. If you say this is the alpha angle, so according to this alpha angle, we can regulate this battery charging voltage. That is first case of phase shift control, that is symmetrical phase shift control. The second one is asymmetrical phase shift control. That means in this case, what we will do is only one half cycle voltage will be controlled. So that is, so this is the complete cycle, half cycle. So this is the negative half cycle dead band. You can say zero level. So this will be controlled according to your output voltage requirement. So this you can say that asymmetrical phase shift control. So in the primary, so what is this advantage of the inverter control is that we need the communication between the primary and secondary, but there is no requirement of the active switches at the secondary side. There is no requirement of active switches such as DC-DC converter is not required, such as active rectifier is not required. The only diode bridge rectifier is sufficient to control the output voltage. So, right? So another way of classification, you can say that without communication and with communication. Without communication is that we will use active rectifier or DC-DC converter in the secondary and we will regulate the output voltage. With the communication is that by controlling the high frequency inverter itself. With the control of this high frequency inverter, we can regulate our output voltage or current for the battery charging regulation. That is, we can refer it as CCCV modes of operation. We can regulate with the help of primary side high frequency inverter. Right? This is about these DC to DC, like vehicle to grid and grid to vehicle application control, you can say. Now, in the real-time scenario, we should have a single stage conversion, right? Single stage conversion means, see, in case of the single phase AC grid to charge this DC, first we should have a filter. Generally, depending upon the voltage level, here we will have a transformer. So instead of this transformer, we will be using a high frequency transformer to reduce the transformer size right over here and to create the isolation between the primary and secondary, right? Generally, in conductive battery charger, instead of this inductive coils, we will have transformer, high frequency transformer. That is what we will be used in DAB. This is dual active bridge converters, which will be used for the battery charging regulation as well as in solar applications, right? So let's assume we have a grid and our intention is to charge this DC battery in EV application, that is wireless power transfer for EV battery charging application. So first, this AC source will be converted into the DC source with the help of an AC to DC converter. You can say it is a diode bridge rectifier, and then we will have a active power factor correction stage, that where we will use a DC-DC converter to regulate to control the power factor as well as to THD. So generally this filter will be used for the THD limitation, and this AC to DC converter itself will have two stages. One is AC to DC conversion and another one is DC to DC conversion, which will be used to regulate this power factor. So as our system demands high frequency, so here whatever the DC is there, that will be converted into high frequency AC, then this resonant capacitor, then this coils, then again resonant capacitor, then AC to DC converter, and then this battery will be regulated with the help of this active rectifier or diode bridge rectifier. If it is diode bridge rectifier, then communication need to be sent to the primary side, so that this inverter will take care of this battery charging regulation, right? So if you see conventionally, how many stages are there? First one is AC to DC, then DC to DC, then DC to AC. So these three stages are there in the primary. So if you come up with any topologies to make it as direct AC to AC, that low frequency AC to high frequency AC, one example is that matrix converter, which have 8 switches, right? For a single phase itself, it will have 8 switches. If you come up with the new topologies to make direct AC to AC conversion, it will be a great research work, you can say, right? And controlling their corresponding to obtain this battery charging, controlling of this matrix converter, and controlling without any communication is also a great research work in this IPT technology, you can say, right? So overally, in single phase AC to single phase AC system, for the IPT system, we have 3 stages, that is multiple stages, which is AC to DC, DC to DC, and DC to AC converter. So in some PFC topologies, you may have single stage conversion, that is also can be used right over here. So this is one where research work can be done. So right now, currently, I am working with this single stage AC to AC converters, and the second research scope which I am currently working is voltage doubler and current doubler converters for the IPT system. So what is this voltage doubler and current doubler converter? Is that see, in market, if you see that 400 volts battery pack and 800 volts battery pack voltages has come. So now we have a system which will be used for only single voltage design, right? Either 400 or 800 volts. Now we wanted to make it as a universal charger which can charge both 400 and 800 volts, right? So that way, though, if you have primary converter which can give you the 400 volts and 800 volts supply to charge the battery, so that will be a good research, you can say, I can say. So on this, we have worked on a three leg converter, which give us the 400 and as well as 800 volts of DC battery charging, right? So this is one example for the driver circuit with which is CPL3101 driver, which can be used for the high frequency of up to 80 kilohertz. Okay. And this is one voltage sensor at the DC output. This is a DC voltage sensor. Okay. If you wanted to do high frequency inverter here, right over here, control, if you want to measure this, then you have to use different sensors to use for the 85 kilohertz, right? And now coming to the final thing, which is safety evaluation for this IPT system. Right. So for real-time implementation, we have to see the electromagnetic interference as well as that you can say electromagnetic interference in the sense here magnetic flux density linkages to the external devices or external uh, body elements you can say, and similarly electric field intensities we have to observe. So this is the one case study which has been performed on human body. So just this entire thing is carried out in the ANSYS Maxwell simulation, so don't worry about that. So let us assume that you have a human body is just lying to the IPT system deployed EV, and your IPT system is working to charge your EV battery. So what will be the interference of this magnetic flux as well as electric field intensity? This is the 50 kilowatts case and 400 volts a battery pack. So where they have observed that the maximum value of the flux density which is interfering with human tissue is that 1.3609 micro Tesla, and similarly electric field intensity is that 3.1443 volt per meter. So is there any impact on the human tissue? It means that there is a one guideline which is International Commission on Non-Ionizing Radiation Protection, which says that the human tissue can withstand less than 27 microtesla, and the electric field should be less than 83 volt per meter. So if you compare these two values here, 3.143 volt per meter and this 83 volts per meter, and this flux density is here 1.3609 microtesla and this is 27 microtesla, which are very far away. So they overall you can say that there is no impact or there is no harm on any human tissue or human body. Similarly, there are literatures which are been performed for the assumption of if the animals like cat or dog has been just lying over between the transmitter and receiver coils, what is the impact on that? So they also have studied those things and it is found that there is no impact on any of the human bodies or animal bodies, which can be really implied. So if you wanted to see whether this uh, really available in the market or not, if you observe, it is already available in the markets. In the Sweden country, they have made already one separate lane for the electric cars to charge while moving itself, and as well as the industries like Vitricity and there is one industry from the Germany. They have already made the products available in the online for the 3.3 kilowatt and 7.2 kilowatt wireless chargers. Okay, we can hope in the coming few years we also can see those products in the Indian market. And if you want laboratory prototypes, I think recently this NAMPAT has introduced in the GEM portal of 1 kilowatt wireless charger, which is already available in the GEM portal by the NAMPAT. Okay, so this is about my presentation about the power electronic converters for the IPT system, as well as the electromagnetic prospects. Yeah, so if you have any questions, and the floor is open. Yeah, anyone have any question? And so we are looking for the research scholars to work in our department. So if anybody is interested, they can reach out our institute in the coming June sessions. So anybody have any questions, please you can post it in the chat box.
Is it completed, sir?
Yes, yes, I am done.
So dear participants, if you have any doubts, you can ask me. You can ask this or unmute your mic and you can ask the question.
If you are uncomfortable in talking, you can post in the chat box also.
Sir, one question is there in the starting box.
Yeah, which wireless charging is more commonly used? So, as you can see that, as I've told you the general classification, so in real-time applications, resonant inductive IPT system is used for EV applications. So in the market, whatever few years back you have seen portable mobile chargers, those also worked on this induction-based wireless power transfers only. And in the market, whatever available, those are resonant inductive power transfer based EV battery chargers. And whatever we are working in my lab, whatever we are working is also the same. Resonant inductive power transfer based IPT systems.
Still any doubt is there?
You can reach out if you have any doubts. You can reach out on my email ID. I'm just posting it in the chat box. Anytime, floor is open.
Okay, sir, better, sir. Sir, in chat box, there is one question.
So in India, anywhere are they using wireless charging? So real-time EV applications are not yet come, but laboratory prototypes are available. So as I have mentioned, NAMPAD has introduced the product which is available in the market. If you are interested, you can go just check in the GEM portal. You can find that the wireless charger, I think 1 kilowatt system with 60 volts battery charging, which is available for the laboratory prototypes, not for the real-time implementation. So in which university institute laboratory model? So if you want really interested to see, you can come and see in my lab. I have 120 volts, 1 kilowatt wireless battery charger setup, which we have done the laboratory model for 120 volts battery, and as well as the voltage doubler, current doubler converters for the IPT systems we have developed it. So if you want to see this, you can visit the NITK. And apart from that, as per my knowledge, this VNIT Nagpur, they also have it under the Professor Ritesh Kumar Keshri sir. And one more place in Energy Trichy, which I have developed, that product is also there.
Still any doubt? Dear participants, still any doubt is there? Okay, sir. Sir, for providing very informative discussion about electric vehicles, charging station, fast charging methods, wireless charging methods, bidirectional wireless power transfer for vehicle to grid to vehicles.
Yeah.
So this session is very useful, sir. So I think this session will enhance the research knowledge of the participants. Thank you.
Sir. Thank you all. Thank you for here listening my session. So thank you. Thank you all.
Okay. Thank you, sir. Now we can disconnect. I capture. Yeah. Dear participants, so next session will be started 10 a.m. tomorrow. So now you can leave the meeting.
Thank you, participants. If you have completed feedback link filling, then you can leave the session. Tomorrow again, we will meet in the same Zoom link at 10 a.m. Dear participants, link is opening. Please retry it once.